All right, so we're talking about spherical triple integrals. So last time we said that our spherical coordinates are. I got to show you my screen, of course. Okay. So we said to find a point, a location in spherical coordinates, it requires rho, distance from the origin, theta, which is our standard trig angle, polar angle that we've been dealing with forever, and then this new angle phi, which is the angle tipped down from the positive z-axis in the direction of theta. So I prefer starting with angle theta. So angle theta is our standard trig angle. 0 is the positive x-axis, sweeping counterclockwise, pi over 2, pi, 3 pi over 2, and back to 2 pi. So that's what theta is. It's familiar, right? And then, so here's the second quadrant angle of theta. Then phi, I like to think about phi next, and that would be the angle tipped down from the z-axis in the direction of theta. Let's make that a little smaller. There we go. So the angle tipped down from the positive z-axis in the direction of theta. That means it's always positive. It's not positive to the right and negative to the left, because it can be in any direction theta, and that value will always be between 0, so 0, and then we get to the xy plane, it's pi over 2, like that, and then down to pi is the negative z-axis. So phi is this new thing that we've not seen before. And phi ranges from 0 to pi. So theta will be our standard angle that goes from 0 to 2 pi, but we have to make exceptions for that if our solid or our region comes across the x-axis, positive x-axis, and skips, like, say, from the fourth quadrant to the first quadrant. Then we need to kind of break this rule. But whenever we can keep theta between 0 and 2 pi, we do. Rho, again, is the distance from the... So once we pick a theta and we pick a phi, so all right, so here's the angle theta is 2.326. That's in the second quadrant, or second octant. Showing 2.3 radians. And then phi is in that plane, tipped down. I'm showing 1.3 radians. And then rho is the distance from the origin. I'm showing 0.95. And so this gives us the point 0.95. Theta is 2.3, 1.3. Okay, and then we showed all the relationships between the coordinates in spherical, cylindrical, and rectangular coordinates last time. We developed all those formulas, which are super important, and not only to be able to use and have from a more memorization standpoint, but really understanding where they all come from. They come from all of our trig relationships, right? Right triangles, sine and cosine, opposite, adjacent, hypotenuse, the Pythagorean theorem. We get all those relationships through that. Okay, and then we found that dv, at the end of class last time, dv for spherical coordinates was rho squared sine phi d rho, and I think typically the the order doesn't matter here. Typically, I do d phi first. I know that it's rho theta phi for points. Typically, when I do the triple integrals, I do d phi d theta. But it doesn't really matter because the limits of integration for phi and theta, 99% of the time, are constants. So when you have constant limits of integration, you can just swap them without doing anything. You just can change the order without fear of anything being wrong. Okay. And then we're going to have some function of rho, potentially rho phi and theta. And then our rho is going to go from rho 1 to rho 2. So we imagine the archer. Now the archer is going to be standing at the origin, firing in all directions, because rho is the distance from the origin in any direction. And then from phi 1 to phi 2, and theta 1 to theta 2. So this is what a triple integral in spherical coordinates will look like. This whole thing is our dv. Rho squared sine phi is, it comes along with the dv, but then it multiplies in with your function and becomes part of what you integrate. Okay, questions on just the form of a spherical triple integral, or just spherical coordinates in general? Any questions? All right, let's do some. So just the rest of the time, we're just going to be doing examples. This will be good class. Here we go. So first example on the easier side. Let's turn off the plane here. All right. We want the limits of integration for the bottom half of a sphere centered at the origin with radius 7. So our spherical triple integral is function times rho squared sine phi d rho d phi d theta. So let's draw it. So we want the bottom half of a sphere. It's actually the bottom half of a ball. The sphere is just the shell. It's just the surface. So like a solid sphere, we have the solid sphere actually, or ball, you could say bottom half of a ball, or solid sphere, centered at the origin with radius 7. So let's sketch that. So it's just going to be the half sphere below the xy plane, with radius 7. Try that again. Like that. So something like that. And now we just got to apply our understanding of rho, phi, and theta to get the limits that are going to get every point in that solid, right? We want to cover every point in that solid half sphere. So what values of rho do we need to cover every point? So shooting arrows from the origin into the solid. What is going to be our range of rho for this half solid sphere?
0 to 7.
7.
Someone wants 0 to 7. Yeah, as soon as, so if it goes through the origin, then as soon as the archer fires, it's in already, right? It's in at 0, and then out at a radius of 7. Okay? And what about phi? So remember, phi is our angle, let's draw it over here. Phi is our angle tip down from the positive z-axis in any direction, right? Or in the direction of theta.
Pi over 2 to pi.
So where is phi going to start? Phi is going to start at the xy plane. That's pi over 2. And where's phi going to end? Phi is going to end straight down the negative z-axis. So that's pi. Okay, what about theta?
0 to 2 pi.
Yeah, so for theta, it's our standard angle. We just need to go all the way around. Questions on setting up the spherical triple integral for this one?
How did you get the pi halves to pi for?
So phi is the angle tipped down from the z-axis. So at what angle of phi do we start hitting the solid?
Oh, okay.
We're going to start hitting it at at the xy plane, which is that's pi over 2.
Okay. that
And then
makes
we
sense.
need all the way down to the bottom. So here's
Okay.
pi equals pi over 2. And that in all directions, 0 to 2 pi.
Okay. Thank you.
Yeah, sure. Other questions? Okay. So if we said last time, this function is a R4 function, like a R4, like a surface in R4. And if we do this integration of a triple integral, we get like net volume of net hypervolume, net four-dimensional volume. Okay, which doesn't, for our purposes as engineers, it doesn't really have a lot of application. So, but what if we wanted to use this triple integral just to find the volume of our solid? If we want to find, the magnitude of the thing we're integrating over, in this case, it's the volume of a solid.
If you took out the function itself and just, not took out the function, but made it 1.
Yeah, that's right. So just like we saw with double integrals, if you make the function equal to 1, you get the area of the region, right? You trick the double integral into finding area. Well, here we by making the function 1, rather than getting a net four-dimensional volume, by making the function 1, we get the volume of that thing in R3. And what is that volume? So volume of the half sphere. Let's find it by geometry, and then let's do the integral and show that they match. So what is the volume of a half sphere?
4/3 times radius cubed.
Okay, that's the whole sphere, and we'll take half of it. Good.
Right.
4/3 pi times radius cubed. Right? Whole sphere is 4/3 pi r cubed. We want half of it. So we're going to get, what, 2/3 times pi times 7 cubed, which is 2/3 pi times, I think that's 343. But either of these, if we can get the integral to be either of these two, then we'll be done. Okay, so let's do it. So we're going to integrate what? First with respect to rho. And so we got, if this is 1, then the rho squared sine phi joins up with the 1, and that's what we integrate. So with respect to rho, our first antiderivative is
1/3 rho cubed times sine of phi.
right. Sine of phi is a constant with respect to rho. So it's multiplied, so we just hold on to it. We do the antiderivative of rho squared, and that's going to be from 0 to 7. And what do we get for that? You get 7 cubed over 3 sine phi. And then minus, you got to, even if it's 0, still plug it in. Make sure you could get a non-zero value here. In this case, we do get 0. So our final answer is 7/3 cubed sine pi. And so now we're going to do the double integral of 7 cubed 3 sine phi. And now we got d phi. And so antiderivative of 7 cubed times 3, or over 3 sine phi, antiderivative is
Negative cosine.
negative cosine, right? And that from pi over 2 to pi. And then we'll have d theta. Okay, so what is that? Plug in pi, we get what? Cosine of pi is -1 times negative 7 cubed over 3 is 7 cubed over 3. And then plug in pi over 2, cosine of pi over 2 is 0. So no thetas here. We're just going to get 7 cubed over 3 theta. Plug in 2 pi and 0 and subtract. 7 cubed over 3 times 2 pi. Does it match? 2/3 pi times 7 cubed. Got it. Check. So finding the volume using a spherical triple integral, we're going to make that function equal to 1. And that gets the volume of that thing that we're integrating over. Questions on this example?
I have a quick question.
Please.
Where did you get the e squared sine phi from?
Rho squared?
Oh, my bad. Sorry. It looks like an e. Yeah, rho
Yeah,
squared.
that was from last class. We derived that this was dv.
Okay, got it. Thank you.
Yeah, so check out last video. dv is not going to just be d rho, d phi, d theta, because d phi and d theta are not lengths. They're not differential lengths. So to change them into differential lengths, we found that we need this factor rho squared sine phi.
Okay, got it. Thank you.
Okay. Other questions? Okay, new example. Okay, a little bit more challenging solid here. So with the integral and spherical coordinates, find the volume of the solid. Consists the set of all points between this equation and this equation in the third and fourth octants. So, what are these things?
Spheres.
These are spheres. Sphere. How can I rewrite those spheres now that we have spherical coordinates? X squared plus y squared plus z squared equals 6. How can I rewrite that sphere? Rho squared equals 6. Remember last time we showed that x squared plus y squared plus z squared is rho squared. And therefore rho equals radical 6. Rho is positive. And then same thing here. Rho squared equals 9. Which means rho is 3. So rho equals 3 is exactly equivalent to this equation. X squared plus y squared plus z squared equals 9. Right? Distance from the origin is 3. Distance from the origin is 3. Okay, so we got spheres centered at the origin with these radii, and we want in the third and fourth octants only. And you remember that our first octant is positive x and y. Second octant, just like the quadrants, we go around counterclockwise. First octant, second octant, third octant, fourth octant. So third and fourth are up here above the xy plane, and then in negative y territory. And so can you imagine this? Between those two spheres and in those two octants, what will that be?
Theta goes from pi to 2 pi.
Well, we just gotta, not yet. So we're gonna try to draw and imagine the solid first. That's gonna be crucial. Like these are geometry problems. We gotta sketch them first. So there's my radical 6 and my 9 or my 3. So between the two spheres, but only in these two octants, maybe is that gonna look like this? Boom, and then this, and then I could kind of join this like this. How'd I do? Is that what you were imagining before I drew it? So how would you describe this, like with something in the world, so we can really see that we see it clearly?
A watermelon slice.
Okay, something like
that is perfect.
yeah, like the watermelon slice, but like all the watermelon's gone, right? It's kind of like just the rind, right? It's just like the rind. Or like an orange quarter, like a quarter of an orange, where you ate all the fruit and just left the peel. Or like a band shell, right? Like, so there's a stage here, and we're listening to some music or watching a play outside, something like that. Okay, So here we go. And if we would say we want to do the volume of that, so the volume of that would be 1 times rho squared sine phi d rho d phi d theta. And rho goes from what to what? So the archer stands at the origin, shoots arrows in every direction into that solid. And where do those arrows enter into the solid? What rho value?
The 6.
Square root of 6. Right? So at 0, there's no solid here away, it's close to 0. We don't get to the solid until that inside of that sphere. And then the arrows exit the solid at 3, right? And then phi. So remember, phi equals 0 is here. And we're going to tip down. And what range of phi is going to hit all the points in the solid? From what to what?
Zero to pi over 2.
I think he's onto something. Right, so 0, we need it at the top here, up the z-axis, and then all the way down to the horizontal plane, xy plane, that's pi over 2. And then theta goes from what to what?
Pi over 2, or pi to 2 pi.
Yep, so here's theta equals 0. Positive y-axis is theta equals pi over 2, right? Top of, this is up, right? Up, top. And then pi, all the way around 2 pi. Okay, so I think we got it. And if we were to find, I made the function 1, so if we were to evaluate this integral, we would get the volume of the solid. Because f is 1. Okay, questions on that?
It looks like the most important thing, like for this and like the homework, is drawing out the graph. It looks like it just helps a lot. It makes it a lot easier. So on the test, we're gonna have to know how to do that.
Mm-hmm. Yeah, and that's been all the way since double integrals, right? Double integrals were all based on those drawing the regions. Super important to get the limits, especially reversing, changing the order of integration. We said that was dependent on make the picture, then use the picture to draw your new limits. So yeah, these are geometry problems. Can't escape that. There's no way to get around that. Okay, now I want to do this. That was spherical coordinates. I want to do the same problem in cylindrical coordinates. I want to do a cylindrical triple integral. Okay, and so what does that look like? That looks like we got our function, and what's our dv in cylindrical coordinates? Remember what dv is?
R dr d theta.
Yeah, r, and then there's a z in there too. dz, dr d theta. So we're going to go what? Bottom surface to top surface. It's going to be our dz. And then we project into the horizontal plane, the xy plane, and do polar. So that was kind of the construct that we had all along for these triple integrals. So notice that with a spherical integral, we don't do this. It's not this projection double integral anymore. It's spherical integrals. It's truly you just take each integral one at a time. So you do the limits for rho, you do the limits for phi, and you do the limits for theta. So we don't conceive of the solid being projected into a plane and then doing a double integral. But all other triple integrals, that's the way we do it, right? So for the rectangular and the cylindrical coordinate double integrals, we're going to go surface to surface and then project into the plane and do the double integral for the region. So that's what we're going to do here. So this is going to be surface to surface, and then the projection into the r theta plane, which is the horizontal xy plane. So I'm going to draw that projection first. It'll be helpful to draw that projection first. So what is the projection of this band shell or orange peel into the XY plane or the polar plane? What is that projection?
Like a half
Like a rainbow.
Is that like a half circle?
Okay, half
like
circle.
a half washer.
Yeah, half washer, something like that. So, and that's in the negative y territory, right? Like that.
Yeah.
Oh, it's doing so good. There we go. That's pretty good. And so then the projection of the solid is this part right here. Is that right?
I don't think so, because the upper part of the watermelon slice, whatever,
Mm-hmm.
it's not being covered by that shaded area. That shaded area only represents like the bottom
Okay.
of the surface.
So you're saying I need more in this projection?
Yeah.
Where? What's the more?
It just needs to be a full half circle.
Right, exactly. All this stuff in here is still part of the projection, right? You got solid all the way to the XZ plane. All this stuff up here projects here, so I'll just fill that in dark. So it's both, right? It's when you press that, when you collapse that solid onto the XY plane, you're gonna get stuff in the donut, but then you're also gonna get all that stuff inside that part too. Does everyone see that? So this whole thing is part of the projection. Okay, so now we're gonna go bottom surface to top surface. What's the bottom surface of this? What's the bottom surface? So this is now my archer. If it's DZ, my archer always fires arrows straight up, but everywhere below the solid, firing straight up in the Z direction.
Is it a combination of two surfaces?
Okay, so what two are you thinking?
It's like z equals 0 and the inside of the inside half sphere or quarter sphere or whatever.
Very
I don't
good.
know.
Yeah, hopefully many others of you saw that when those arrows enter in close to this outer radius here, they're going to enter into what? Z equals 0. That's the horseshoe or the donut where I've crosshatched. But when you're closer to the origin, the arrows go through the XY plane but haven't reached the solid yet. They don't reach the solid until the inside sphere, and that's for the dark part. Does everybody see that? So here's the crosshatched. That's the crosshatched part. That is Z equals 0. So sometimes arrows enter in at Z equals 0. Other times they enter into where? Closer to the origin. They enter into Z equals what? So it's this sphere. So it's Z going to be what? Square root of 6 minus x squared minus y squared, which is what?
So that's like
6 minus radius squared.
6 minus r squared. What about the top? What about the top surface where the arrows exit? Is that split up or is that all one top?
Is it all square root of 9 minus all squared?
Yeah, it's all gonna be the top, the bigger sphere. It's the entire top. All the arrows will exit out of this sphere. Can you see that? So sometimes the bottom surface is 0. That's the crosshatch. That's the donut or the half washer. Sometimes the arrows enter in higher up at the smaller sphere. That's closer to the origin here. And all the arrows exit out the bigger sphere. So the outside double integral they're gonna be for where, where do the arrows enter in at 0? So for what r and theta values do we enter in at z equals 0? R goes from what to what? Radical 6 to 3, you should be thinking, right? So it's, the crosshatch is r going from radical 6 to 3, and theta from what to what?
Pi to 2 pi.
And then, where do we enter into, for what r values do we enter into the bottom, the smaller sphere as the bottom surface?
0 to square root of 6.
Right. That's the dark shaded region here, 0 to square root of 6. And that from pi to 2 pi. Again, if we want volume, we make f equal to 1. But we're going to add these two together. Why we need two triple integrals? Because the bottom surface with respect to z is split up between z equals 0 and z equals that smaller sphere in there when you're closer to the origin. Any questions on the cylindrical version? So what is it about this surface, this solid, that makes it so easy to do or so much easier to do in spherical coordinates and more complicated to do in cylindrical coordinates? What is it about this solid that lends itself to spherical coordinates?
It's spheres. Are spheres.
Based on spheres, right? So it's so rho equal, look at this equation in rectangular coordinates for a sphere. Long and complex. 3 variables needed, squares. Look at it in spherical coordinates. Rho equals 3. Boom. Rho equals radical 6. So when your solid is based on spheres centered at the origin, spherical coordinates are going to be much simpler because that's what it's based on. Based on values of rho gives you a sphere centered at the origin. Cylindrical coordinates is based on mostly on r. R is what? Distance from the z-axis. And if you have a constant r at all heights and directions, what kind of thing do you get? You get a cylinder centered on the z-axis, right? A constant, say r equals 8. That's a cylinder centered on the z-axis. So solids that are based on something like this will lend themselves more nicely to cylindrical coordinates, cylinders. Solids that are based on spheres centered at the origin will lend themselves most nicely to spherical coordinates. Okay, other questions? Got one more good example here. Do the limits for cylindrical coordinates make sense on this solid here? Okay, here we go. So now we want to set up the integral in spherical coordinates. Oh, so that's what we're gonna, this is the function we're gonna integrate. My f, okay, so that's my f, over the solid defined this way. Inside x squared plus y squared equals 4, below z equals 5, outside x squared plus y squared plus z squared equals 4, and in octants 1 through 4 only. So let's go through each one of these and sketch them. What's x squared plus y squared equals 4?
That's cylinder in the z direction.
Good, right. It's the cylinder based on the circle. X squared plus y squared equals 4. That's the circle of radius 2. But then it extends in the Z direction, the missing variable. So this is a cylinder. Like that, okay? And below Z equals 5. What's Z equals 5?
Horizontal plane.
Horizontal plane at 5, and we'll just put 5 right there, okay? For just, because that's where I stopped the cylinder, so we'll make that Z equals 5. And then outside of x squared plus y squared plus z squared equals 4. What is that? X squared plus y squared plus z squared equals 4.
It's a radius of 2 sphere.
Yep. So, and notice that the radius of that sphere is the same as the radius of the cylinder, so it's going to sit right here. All right, and so outside means, so if it's inside the cylinder and outside the sphere, and this basically means octants 1 through 4 means z is greater than 0. So it means up here. So do you see what the solid is? It's inside the sphere, below the plane, or inside the cylinder, below the plane, and outside that sphere. Okay, so what do we think? This going to be more suited to cylindrical coordinates or spherical coordinates?
Cylindrical.
Definitely cylindrical. Let's do it first. We got, and so what is x squared plus y squared plus z squared in cylindrical coordinates? X squared plus y squared is?
R squared.
So we got r squared plus z squared. So that's x squared plus y squared plus z squared. And we'll have r dz dr d theta. Remember, r comes from the dv. But then when you integrate, you'll multiply times your function. Okay, dz, bottom to top. Archer fires below into the solid. Do the arrows enter in one surface or more than one surface?
More than one.
More than one.
Oh.
Right, just the one, we only just sphere.
Yeah, just right. Everywhere in the solid, you're always going to enter in the sphere, right? You're going to pass through the xy plane, and then you're always going to enter in the solid through the sphere. Okay, so what sphere is that in? What, in cylindrical coordinates? Z equals?
Square root 4 minus x squared plus y squared.
Yep.
Oh, then minus r squared, r
Right.
squared, plus r squared.
Minus x squared minus y squared, which is minus r squared. And then where do the arrows exit? Z equals?
5.
5. Okay, projection into the xy plane is simply the whole disk of radius 2. So when we flatten that thing on the xy plane or get its shadow, dr is 0 to 2, theta 0 to 2 pi. Disk of radius 2 in the xy plane. Questions on cylindrical coordinates? Pretty straightforward. The only thing that's slightly weird, but not a problem at all, is our sphere, right? All right, now spherical coordinates. What do we got in spherical coordinates? We got, first of all, x squared, our integrand, x squared plus y squared plus z squared is going to be?
Rho squared.
Rho squared, and then we're going to have another rho squared sine phi, d rho, d phi, d theta. Okay, here we go. So now the archer for rho, the archer stands at the origin and fires arrows in all directions. So where will those arrows enter into the solid? One surface or more than one surface? Entering in.
2. That's here.
To get into this surface with arrows, it's going to be always through the sphere from that point, all directions. So that sphere is rho equals what?
2.
That was our rho. This is our rho equals 2 sphere, right? X squared plus y squared plus z squared equals 4 is equivalent to rho equals 2. Okay, where will the arrows exit? So they pierce into the sphere, into the solid. Where will the arrows exit?
Yeah, exit at z equals 5.
Okay,
So we have to,
exit at z equals 5.
oh, and also like the side of the cylinder.
It depends, right? So do you see that those arrows are going to exit out 2 different surfaces? Sometimes, say for lower values of phi, up here near the z-axis, those arrows will exit out z equals 5. For higher values of 5, those arrows will exit out r equals 2, the cylinder. What does it mean for a triple integral?
Do we have to break it up then?
We got to break it up because the exiting surface for rho is different. It could be z equals 5. It could be r equals 2. It always enters in rho equals 2. Okay, so the question is, so sometimes it exits out z equals 5, but the problem with that is 5 is not a rho. We need what rho is for z equals 5, and we need what rho is for r equals 2. So if you remember from last time, so if this is r, and this is z, and this is phi, then what does, and this is rho, how do we relate rho and z together? Z equals?
Rho cosine phi.
Yeah, we derived that last time, but we can just do it again here. And then r equals?
Rho sine phi.
Rho sine phi. Okay, so if z equals 5, that's a constant, z equals 5, then what does rho equal if z equals 5?
5 over sine phi.
5 over
Cosine.
cosine, right? So solving for rho, we're going to get 5 over cosine phi.
How did you know to draw that triangle?
That's what we did last time. So we derived the relationships between all the different variables. So I'm just kind of redoing it again.
Okay.
So z is distance up, r is distance out from the z-axis, rho is distance from the origin, and that angle between the rho and z is our phi angle. So this is kind of a little bit review. So it will always be that. This is always true. Z is always up, r is always out from the z-axis, rho is always your distance to that point, and phi is always that angle. All right, and so then what about r equals 2? So sometimes, right, so sometimes like for these low values of phi, the arrows pierce in through the sphere and then out through z equals 5. But then sometimes the arrows pierce into the solid through the sphere and then out through r equals 2. And what is rho when r equals 2?
Is it 2 over sine phi?
Yeah, right? So we know r is 2 for this problem. Solve for rho, 2 over sine phi. It's not too bad. So what's happening? Rho is variable, right? So as phi starts to increase, rho increases, right? The distance to that z equals 5 plane increases according to the angle phi. So it's a function of phi. And then likewise, as phi keeps increasing, the distance to the cylinder decreases according to 2 over sine phi. All right, so now for our measurements of phi, what are we asking? We're asking for what range of phi do we exit out that top plane z equals 5? So for what range of phi? So it'd be phi equals 0 to what? 0 to this intersection, right? So this angle of phi, call it phi 1, is that angle of phi where we're done with this plane and we start with the cylinder. So that height is, what is the height? The height is 5. The radius is 2. So that's my opposite side is 2, the r. My adjacent side is 5, so what angle is phi 1? Won't it be arctangent of 2/5? Does it make sense? Opposite side is 2, adjacent side 5. That's that angle. Where's the breaking point? And so we're going to do opposite over adjacent, inverse tangent. So when phi is 0 to that angle, we're exiting out z equals 5. And then starting at that angle, tangent inverse of 2/5, all the way down to what angle?
Is it pi over 2?
Yeah, pi over 2. All the way to pi over 2, we exit out of the cylinder, r equals 2. Here's the row corresponding to r equals 2. And then all this from 0 to 2 pi for theta. Okay, so here we see a solid that's formed like a cylinder parallel to the z-axis, therefore cylindrical coordinates fast and efficient and easy. Spherical coordinates not fast and efficient, but a great problem to test your understanding of spherical coordinates.